Step E, the pH at the equivalence point. Well, this is the very typical types of titration question. You just need to know everything. The pH at equivalence point, what is the solution at equivalence point? At equivalence point, all the weak acid has been converted to the conjugate base. Well, look previously, what is the total moles of substance of weak acid? 2.1 millimole. That means at the equivalence point, you have exactly 2.1 millimoles of the conjugated base. So, E at equivalence point, let's say EP, you have 2.1, we can put a 0 there, millimole, not mole, millimoles of the conjugated base. Well, what is the volume? The volume is where you start. 20.0 the volume for the weak acid, and the volume you add sodium hydroxide, which is the answer in step number B, 16.8 milliliter. Well, the total 36.8 milliliters. Okay, well, you have the total moles of substance. You have the total volume. What will be the concentration? The concentration here for sodium, let's see, concentration sodium A, essentially it completely dissociated since it's a salt. A equals 2.1 millimole over 36.8 milliliter. If you want to say 2.10, if you want to keep 3 significant numbers, same time we have 2. So this one, we got 2.1 divided by 36.8 equals 0.057, let's say 0.0571. Smaller? 0.0559 is also okay. Alright, now we have this. We have this, we have its concentration. Now, let's write this equilibrium. The equilibrium become A minus, which is the base. If it's a base, plus water, so that's the aqueous solution. Equilibrium, write the double arrow sign. Give you the weak acid aqueous, then plus hydroxide, aqueous. If you want to write the S table, well, we can write S table ICE. Let's say this is 0.0571. This is 0. This is close to 0 at the beginning or at the equivalence point. The change negative x, x, x. Now here 0.0571 minus x, x, x. The setup is exactly the same as the weak acid dissociations in step number 1. But here you cannot use Ka since this is a base, weak base, A minus. You need to know what is the Kb of A minus. Well, the relationship between Kb of A minus equals 1, actually not 1, Kw over Ka of Ha. Then let's write Kb. So Kb equals 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. If you see 1.00, that's okay. To keep the right significant numbers. So in calculator, 1 E 14 negative divided by 1.8 exponent 5 negative. What they give you? 5.56, or let's say 5.6 times 10 to the negative 10th power. Alright, now we have this. What would be the x? So in here, the x is hydroxide equilibrium concentration. So hydroxide equilibrium concentration equals x equals, how can we do this? Well, the same setup as the first one is essentially the square root of Kb multiplied by the initial concentration, which is 0.0571. Then take the square root. Let's solve this. Now we still have the Kb here. Let's multiply by 0.0571. Give us the product 3.17 something something something. We need to take the square root of this. Again, shift x squared to give you the square root. It gave us 5.6 times 10 to the negative 6th power. 5.6, if you want to put this in one extra significant number, it's alright. 63 times 10 to the negative 6 power. Then, okay, so this is concentration in molarity. What would be the pH? You can calculate pH using Kw over hydroxide concentration, or you just simply calculate pOH, which that's my preference, equals negative logarithm, just push logarithm, 5.25. Then what will be the pH? 14 minus pOH. Alright, you just see 14 minus this, just add 14. Since this is negative number, give you 8.75.